Namaste, students, and welcome. Today, we're going to tackle a very important topic from our first unit, electric charges and fields. The name is continuous charge distribution. Now, don't worry about the big name. It's actually a very simple idea, but it's also a super powerful tool that helps us solve some really complex physics problems. I'll make it so easy for you, it will be completely exam safe.
Okay, let's get right into it. We've all studied Coulomb's law, right? It's perfect when we have two tiny point charges, Q1 and Q2. But what happens in the real world? What about a big object, like say this plastic ruler? If we charge it by rubbing it on our hair, how do we calculate its electric field? Can we still use that simple Coulomb's law formula?
Now, look at this. This shows the problem very clearly. On the left side, you have 2-point charges. The distance r between them is just one single value. Simple. But now, look at the charged rod on the right. If we want to find the force on that test charge Q, the distance r from the top of the rod is different, the distance from the middle is different, and the distance from the bottom is also different. You see, every tiny piece of the rod is at a different distance. So which r are we supposed to put in our formula? We can't just pick one, can we? This is the big problem we need to solve.
So to state it officially, the big problem is how to deal with these macroscopic, or you can just say large-scale charged objects. The charge is spread all over them, and it's practically impossible to find the effect of every single electron one by one. So we need a smarter way.
To understand this smarter way, let's take a very simple analogy. Imagine you're in an airplane and you're looking down at a beach. What do you see? You see a smooth, continuous yellow surface, right? It looks like a single sheet of color. But what happens when you land and you walk on that very same beach? You realize it's not a smooth sheet at all. It's actually made of crores and crores of tiny, separate grains of sand. Well, electric charge on a big object is exactly like this. At the microscopic level, it is grainy. It's made of individual electrons. But from our normal macroscopic view, that graininess just disappears.
And that's our solution. In physics, we do the same thing we do with the beach. We just ignore the grainy nature of individual charges. As our NCERT textbook says, we treat the huge collection of these tiny charges as a smooth, continuous charge distribution. It's like we've smeared the charge evenly over the object, like butter on toast.
Okay, so we've decided we're going to treat charge as a continuous smear. But how do we actually work with it? How do we calculate things? Well, for this, physicists invented a very clever shortcut. It's a tool called charge density. And this, my friends, is the key to solving all these problems. So what is this charge density? Don't worry, it's nothing complicated. It's simply a measure of how tightly the charge is packed. Is the charge packed along a line, or over an area, or throughout a whole volume? It's just a number that tells us the concentration of our charge smear. Very simple, very practical. Now, since objects can have all sorts of different shapes, this smear of charge can happen in 3 different ways. And for each way, we have a special type of charge density. Let's have a look at them.
It's really simple. If the charge is spread along a one-dimensional line, like on a thin wire, we call it a linear charge distribution. If it's spread over a 2-dimensional surface, like a sheet of metal, it's a surface charge distribution. And if it's spread throughout a 3-dimensional object, like a solid sphere, we call it a volume charge distribution. 1D, 2D, and 3D. That's it.
Now, this slide is your exam safe zone, so please pay close attention. For linear charge density, the symbol we use is the Greek letter lambda. It's defined as a tiny bit of charge, dq, spread over a tiny bit of length, dl. And its unit is coulombs per meter. For surface charge density, the symbol is sigma. That's the tiny charge dq on a tiny area, ds. The unit is coulombs per meter squared. And finally, for volume charge density, the symbol is rho. That's the charge dq inside a tiny volume dv, and its unit is coulombs per meter cubed. You must remember these symbols, their formulas, and their units. They are very important for your exams.
Great, so now we have our new tool, charge density. But how do we actually use it to calculate the total electric field of a big object? The answer is a powerful mathematical method that becomes very simple if you just think of it as a recipe. And that method is integration.
So listen carefully. This is the 4-step master method. It works for any shape. Step 1. You look at your charged object, and you choose a tiny element on it, a small length dl, a small area ds, or a small volume dv. Step 2. You find the tiny charge dq on this tiny element using our density formulas. For example, for a line, dq will be lambda times dl.
Step 3. Now this tiny charge dq is so small that we can treat it like a point charge. So you can write the formula for the tiny electric field dE that comes from this dq using our good old Coulomb's law. And step 4, to get the total field E, what do? We just add up the effects of all these tiny little pieces. And what is the mathematical way of adding up infinite tiny pieces? Exactly. Integration. You just integrate dE. That's the whole method.
And look here, this is exactly how we set it up for our charged rod. We want the total field, E, so we integrate the tiny field dE. Now what is dE? It's k times dq upon r squared. And what is dq for a rod? It's lambda times dl. So we just substitute that in. The total electric field E becomes the integral of k times lambda dl upon r squared. And we integrate over the entire length of the rod, from its beginning at 0 to its end at L. See? We just followed the 4-step recipe.
All right, this next section is very important. I call these the silent killers. These are very common mistakes that students make in exams, which cost them a lot of marks. Let's make sure you don't fall into these traps.
Trap number 1 is the most common one. A student sees a rod with a total charge Q, and they think, this is easy. I'll just take the distance to the center of the rod and use the formula F equals KQ by R squared. This is totally wrong. Why? Because as we saw earlier, different parts of the rod are at different distances. You cannot just average it out like this. The correct idea always is that you must integrate. There is no other shortcut.
Now for the second trap. Many students just assume that the charge density is always constant or uniform. In the easy problems, yes, it often is. But in good questions, the density might change with position. For example, a question might tell you that lambda is not a constant, but lambda equals k times x. This means the charge gets denser as you move along the x-axis. Does this change our method? Not at all, and that's the beauty of it. Our 4-step integration method still works perfectly. You just put kx in place of lambda inside your integral. So my advice is always read the question carefully.
Now before we summarize, I really want you to appreciate why this idea of continuous charge distribution is not just for this one chapter. It is a fundamental super tool that you will use again and again in physics.
If you master this idea now, you are making your life much easier for future chapters. In the very next topic, Gauss's law, you will absolutely need to understand surface charge density. When we study electric potential, we will use this exact same integration method to find the potential of a charged ring or a disk. And even much later in magnetism, a very similar concept called current density will appear. So the effort you put in today will pay you back many times over.
Okay, so let's quickly summarize the key takeaways from today. First, for large objects, we treat charge as a continuous smear, not as individual points. Second, charge density, lambda, sigma, and rho, is the tool we use to describe that smear. Third, our master method for any problem is to break the object into tiny pieces, find the effect of one piece dq, and then integrate. And finally, the most important warning, never, ever use the simple Coulomb's law with the total charge Q for a large object. You will get 0 marks for that. Always, always integrate.
So we started with a simple charged ruler, and we ended up with a powerful method that can handle any shape or any charge distribution. Now that you have this super tool of integration, I want you to think about what's next. How can we use this amazing power to understand more complex devices like capacitors, or even unlock the secrets of the structure of matter itself? Well, that is where our journey in physics goes next. Thanks for joining me today.